So what did we see last class? So the main thing we saw was how you solve recurrences. Okay? So you have an algorithm that is a recursive algorithm, and we saw how to analyze its running time. Okay? And the way we did it was to construct what is called as recursion tree. Okay, which so we constructed a recursion tree, and then we showed how you can unravel it to get the running time. Okay, so and there was this very clean way of just keeping track of the cost at each level, and then you add it up over the level. Okay, so at the last level you have to keep track of what the base case contributes. Okay, so that is what we saw last time, and we saw multiple examples of this. And we also saw fast integer multiplication. We saw that there's a non-trivial algorithm that gives an n to the 1.5 time algorithm. And this was one of these tricky examples of divide and conquer. Okay. So this is what we did last time. And one quick announcement. So homework 1. So in general, homeworks will be due on Thursday, and they will be due once in 2 weeks. Okay. So homework 1 in particular will be out tonight, and it will be due 2 weeks from now. So, and the hint is start early, because there will be all these LaTeX type issues that will come up. You don't want them to come up in the last minute. Okay, good. So what are we going to do today? So today we're going to look at essentially two things. One is how to find the median of n numbers. Okay, so this is one of these problems that is it has a tricky solution, and it's hard to come up with it at first sight. Okay, so unless you see it, it's very difficult to come up with it. So we'll see that, and we'll look at what's called dynamic programming. Okay, so many of you might have seen this median finding algorithm. So we'll kind of rush through it. So firstly, has anyone not seen this median finding algorithm at all? Okay, so there's a bunch. So there's, we'll see it in enough detail that you can construct all the solutions. Okay, so and part of the homework will be about this. Okay. So actually one other thing I wanted to mention about the homework, which is that there will actually, not all problems will be like puzzles type. Some of them will be things I would have liked to cover in class. So these will actually be standard things. You can look them up, but I would advise you to write all the solutions on your own. Okay, so you can look them up if you want, and actually the advice is to figure it out on your own and write it. But if you really want to, you could look it up, but make sure you write all the solutions yourself. Okay? Because these are things which, if we had a longer class, we could have covered them, but it's, there's only so many things you can do in a semester. Okay, so let's go to the median. Okay, so what is the median of n numbers? So you have an array. Okay, so it's not sorted. So you just have a bunch of numbers, a0, a1 up to an minus 1. Somebody commented that I always use A1 through AN, so I thought, and it's non-standard, so I thought I'll make it standard. So we have this array, and you want to find the n over 2th greatest, smallest number. Okay, so if you order them such that in increasing order, okay, so you have some b0 less equal to b1. Then you want to find the middle element of the sorted array. So this is the problem, and let's see. So this is also one of these problems where we'll use this unlikely recipe, which is, you want to solve this problem of finding the middle number. Okay, and what we'll do is solve a more general problem, which is a problem of finding the kth smallest number for any k. Okay, and so this is called the selection problem. Yeah, sorry I wrote here, but can you all read the text? Okay. So we'll solve this problem where you actually want to find the kth smallest element, and k is a parameter, and then setting k equals n over 2 will give you the median. Okay. So sometimes when you're designing algorithms, you might want to come up with an algorithm for a slightly more general problem. Okay. So because it might help you do divide and conquer and things like this. Okay. So this is an example that illustrates that. Okay, so let's do this. So is this selection problem clear? So we have an array and you are given a number k. You want to find the kth smallest element in this array. So what's the trivial algorithm for this problem? Like, can you come up with an n log n time algorithm for this?
Sort it.
Yeah, you just sort it and you find. So this is trivial. So always when you have a problem to solve, you've got to first come up with some trivial algorithm. Okay? So it's like, you have a foothold of a problem, and then you try to come up with something nice. So okay, and then you have the usual question. So when can we do better than this? Okay? And the goal is to do something like O of n. So you don't want the additional log n factor. So note that you can't do better than O of n. Why? Yeah, you have to see all the input, right? So that itself is O of n. So this is as good as it gets. Okay. So how do we go about this? Right? So it seems tricky because without sorting, how do you figure out what is the kth smallest without knowing everything before it, right? So that's the tricky thing here. So let's start thinking about this. Okay, so and I want to give a hint. Okay? So suppose I tell you, okay, so I give you the rth smallest number. Okay, I don't tell you what r is. The only thing I tell you is that r actually lies between n over 4 and 3n over 4. Okay. So what I am interested in finding is actually really the middle element, right? So what I am telling you is I give you a number and I guarantee that it's roughly in the middle. Add these numbers in sorted order. Okay. So this is A1 could be somewhere, A0 could be somewhere here, A1 could be somewhere here, 2 is here, and so on. So this is the sorted order of these numbers. Then what I am telling you is I'll give you some number out here such that there are n over 4 numbers over here and 3n over 4 numbers over here. Oh no, sorry, at least n over 4 here and at least n over 4.
We can use the quicksort partitioning method to find it.
Yeah, so let's, and what does that mean?
In quicksort, whenever we find one pivot and we arrange it, then the pivot goes into the middle place, the proper place.
But in this case, you don't know that this is exactly the middle one, right? You want to find the middle one.
Yeah.
Okay? So you know it's roughly there. So this is roughly the idea. Okay, so yeah.
I haven't got it out. So previously you said that sorting is a problem because it's n log n and we want to find it in n. And now you are already given the sorted list. So what's the point here? So you are
No, this is not the sorted list. This is a hypothetical. This is a mental example. I mean, it's a mental experiment in some sense. Okay, so when you try to analyze algorithms, right? So this is all done just for the purpose of analysis. Okay. So you are saying that I'm just pictorially telling you what it means to give a number that is rth smallest. Okay. So how I give you this number, I haven't told you yet. Okay. So suppose there is some procedure for finding approximately the smallest, the middle element. Okay. So something in, which is not in the two extremes. Okay. The question is, can that help you, okay, to come up with a faster algorithm? So this figure that I drew is only for the purpose of analysis. Okay. So that's a good question. So this is often something that one should keep in mind. Okay. So when you're analyzing an algorithm, you can assume you know everything about the instance. So and you have to show that your algorithm can do something good with this. So all right. So okay. So the idea is to follow roughly what he said, okay, which is that okay, I know that this I know this number. So suppose I call it a sub t, okay. And I know that a sub t has it's somewhere in the middle, right? So this is a sub t. I know that there are enough elements to the left, there are enough elements to the right. Okay. Now, the question I want you to ask is, from here of the problem, okay? So you want to find the kth smallest in the full array, right? So now I tell you somebody who is roughly in the middle, okay? Now, what would you do, right? So for instance, suppose k is n over 10. Then what would you do?
N over 10.
So sorry, r is k is n over 10 and r is somebody between n by 4 and 3n by 4.
You will take that array on the smaller part.
Yeah, exactly. So what you would do is you would scan through the full array, figure out who all are less than this guy, and you know that there are at least n over 4 of them and there are not too many of them. Okay. And only in this smaller part you will try to search for this guy. Okay. So scan the whole array. Collect elements less than 80. And this is in the case when k is n by 10. Okay, so I'm just simplifying this. You can do this for in general for any k. Okay, so scan this array, collect elements that are less than 80, and let's call this array B. Okay. And what do we know about the size of B?
K.
I mean, it is actually R because R is that, and R, you know, lies between n over 4 and 3n over 4. So in particular, okay, you know that B size of B is less than or equal to 3n by 4. Okay, and you know that your n by 10th element has to lie in this 3n over 4. Okay. So now you can recurse, right? Because you can recurse on B and say that, okay, I want to find the n by 10th, which is the kth element in B. Okay. So you can recurse and say find in B the kth element. And in this case you can do it because you know that n by 10 is actually strictly smaller than n by 4. So if this had happened to be n by 2, then you have to be a little bit more careful. Okay? Because what if R is actually, let's say R is I don't know, n by 4. Okay? So R we know lies between n by 4 and 3n by 4. We don't exactly know what it is. Okay? But we'll find this in the first step. The size of B is exactly R. And if you find that the element you want to find is not in B, then you know that the complement of B should have what you are looking for. Okay. So you can figure this out in a bit. Let me not go into the details. But roughly speaking, what you can do with this information is that you can reduce the size of the array you are searching in to a factor 3n over 4. Okay. So if you have this information, you can always recurse on an array of size 3n by 4. Okay. Smaller than or equal to 3n by 4. Okay. So this is like an exercise to convince yourself that this can be done. Okay, so assuming this can be done, okay, so what recurrence does this give you, right? So what we are doing is, we are doing this scanning the array, collecting elements. How long does that take? This takes O of n time, right? Because you just go left to right, collect elements that are smaller than this middle guy. So we have this recurrence which basically says t of n is less than or equal to t of 3n by 4 plus O of n. Yeah.
Can you explain this with a set of, say, 10 real numbers?
Yeah. So that will be okay. I have to come up with a blank slide, so give me one. Okay, so so let's think of k. Remember, k is the kth element that you want to find. Okay, k is one goal is to find kth element. And you have a bunch of numbers. Okay, so let's draw them on the line. Okay, so since you have this, and you have 1, 2, 4, 6, 7. Okay, so let's say these are the numbers you have, and k is the third smallest. Okay, so I want you to find the third smallest one. And what I give you is some element.
It is sorted.
Anything wrong?
The array is sorted.
No. So these are not the real indices. Okay, so like A0 could be 2, A1 could be I don't know, 1, and so on. Okay, so as I said before, so when you are analyzing, you can think of you can basically keep in mind the sorted array. Okay, so these are the actual numbers that are in the array. Okay, and what I told you is, I just told you some number which I told you is roughly in the middle. Okay, so suppose I gave you 4. So you know that so I know that 4 is roughly in the middle. So then what I would do is, I would go through the array, figure out who all are less than this 4. Okay, so I'll go through the array in terms of these A's, right? So this could be A0, A1, say A2, A3, A4, A5.
I have a question.
Yeah.
You say roughly in the middle, so does that mean in the middle of the sorted array or in the middle of the actual?
In the middle of the sorted array, that's the point. In the middle of the actual array, you can always find it.
Okay.
Right? So that's what I mean. So that's why that's the formal statement. I tell you the rth smallest number, okay, where r is in this range. Okay, so that implicitly means that it's in the okay. So this is the procedure. Okay, so I look through, and I look through the array in this array index order, A0, A1, so on, and I find everybody who is smaller than or equal to 4. Okay, so in this case, this B will actually be in the same order as this A's, right? So this one, all these things check off. Okay, so I'll first have A0, which is 2. Okay, then I'll have A1, which is 1, then I'll have A4 which is minus 1, and then I'll have A6 which is minus 4. Okay, so this is the array B that I'll produce. Okay, so B will be in the same order as A. And then I observe that B has size bigger than 3. Okay, so I observe that size of B is bigger than 3. So if I have to find the third smallest element in A, I know that it's going to be in B. Okay. So I know that, okay, so what I will do is find in B the third smallest element. Okay. And this is the procedure. And if suppose you had k equals 6, okay, then you will see that, okay, B has size only 4. I wanted to find the 6th smallest in A, right? So I've got to look in the complement of B. Okay, so I'll form this new array C, which is things that are bigger than 4, bigger than or equal to 4. Okay, so I'll form A2, A3, A5. So 4, 6, 7. Okay. And here, if I want to find the 6th smallest in the full array, then it's like finding the 2nd smallest in this smaller array, right? So I'll just do find in C, so k minus the size of B. Okay, so this is the formal claim. Okay. Because size of B elements have already been taken out, and the leftover is this. So yeah, I just wanted to avoid writing the formal algorithm, but this is the formal algorithm. Okay, so you just form the sets B and C. Okay, and if k is bigger than size of B, then you find in C, and if k is smaller, you find in B. So this is a simple algorithm. Okay, so everybody clear how to do this? Yeah.
Is there a way to find the smallest element given we are not given the Rn smallest element? Like they have taken the assumption.
Yeah. So I'll get to that. Okay, so what I want to say is, suppose I tell you what the rth smallest element is, then I want to convince you guys that the problem becomes easy. Okay, and this is the analysis too. Okay, so what you get is T of n smaller than or equal to T of 3n by 4 plus O of n. The O of n is the amount of time it takes you to find these B's and C's. Yeah.
So here we have given the rth element as it's in the range between n by 4 to 3n by 4, right?
Yeah.
So n by 4 to 3n by 4 is the non-sorted array.
In the non-sorted you can always find it. That's also the question that he asked. So rth smallest element in the full array basically means in the sorted thing also it's between n by 4 and 3.
So does that mean we need to take the middle element between n by 4 to 3n by 4 as r? Because we want to know r position also, right? So exact r position to find the k. When you want to compare the two small arrays.
Yeah. So what I'm saying is, you don't know what r is. Okay, somebody just gives you an element and says, hey, this is the 10th smallest element or something like this. Okay. Actually, they don't even need to tell you that. They just guarantee you that this number, this is the rth smallest element for some r in this interval. Okay. And the question is, can you use this information? And we'll see why that's useful why that can easily be done in a second. Okay. But suppose somebody told you this. All I'm saying is you have a fast algorithm for doing it. So then it is this, and then this recurrence, I guess you can all, so this will be one of the homeworks, that this kind of recurrences solve to O of n. Okay, so that's, so the point is to note that you have this geometrically decreasing thing, okay, so, and you have this one term over there. Okay, so one term on the right. And you have this n going to 3n by 4, next time it go to 3 over 4 squared times n and so on. So you can observe that this adds up to O of n. Okay, so this is a homework. So as I said, the homework will have a bunch of recurrences. So one of them will be of this form. So, alright. So if somebody gave you a roughly middle element, then things become easy. Yeah.
For B, do we have a new B for each set?
Yes. So you will call it with a set of a certain size. But one guarantee you have with this process is that the size is strictly smaller than say n by 2. So the size
for new set, like you find we find a smaller set of new numbers, we have a new B for those sets.
yes. And when you recurse, you'll have a different p. Okay. So everybody clear with the algorithm, by the way? So yeah, this is the detailed, I guess, the steps. Okay. So what was key to our analysis? You wanted to find the rth smallest number, where r lies between n by 4 and 3n by 4. Right? So now, one question you should always ask is, we won't analyze this very seriously now, but what happens if I have this array, and I pick a number uniformly at random in the array? Okay, so I pick an index at random, and I pick it uniformly at random. Okay, so the thing to observe is that when you pick something at random, it doesn't matter if it was sorted or not. Okay, because you just picked one index. Okay, so you can again go back to thinking about this picture. You have a bunch of numbers, and what I'm asking you is, if I pick one of these guys at random, what is the probability that I'm in this middle n by 2? Okay, it's half, right? So with at least a half probability, I'm actually bound to find an element that is actually good. Okay? And this is a super fast step, right? So it turns out you can actually formally analyze this algorithm. Just randomly pick an element and use that as the thing, and as this middle element. Okay, so as this AT that we used here. And turns out this actually works. Okay, so this we'll get to sometime towards the later part of this class. And this is what people do in practice. They actually don't, use this more complicated algorithm that we'll see now. Okay. So this works in practice.
I've got a question.
Yeah.
So does that always give you the right answer, or is there an error associated with picking?
Yeah, that's the point. So you will only succeed with some probability. Okay. So now what you can say is,
But that can be always fixed by running multiple versions.
exactly. So once you find it, you see if you are roughly in the middle, and you can fix this, okay, and keep doing, okay, and you can show that the probability that you do some k steps goes off as 2 to the minus k or something like this, and then if you compute the expectation, it turns out to be linear. Okay, so we'll see that towards the end, but if you've done some probabilistic analysis, this is reasonably straightforward. Okay, so we'll do that in the later half of the course. Okay. But it's good to keep in mind. Okay, so when you're trying to come up with a intricate algorithm, just try these things where you say, okay, what happens if I pick something at random? Is there a reasonable chance that I'm lucky? So this is there. Okay, so now can we do this deterministically? Okay, so can we do this in such a way that you are guaranteed to always work? So that's what we will see now. Or rather we will outline now, and this will be part of the homework. Okay. So what is the goal? So our goal is exactly this. So you are given an array, and you want to find a number that's roughly in the middle. Okay, the question is, how quickly can you do this? Yeah, and roughly in the middle means formally it's the rth smallest, and r is in that. Okay. So let's think about this problem for a little bit. Okay, so let's. So what is the first idea, right? So you just want to find some number that you know has, has this property that there are n by 4 numbers in the full array that are smaller than it, and n by 4 that are bigger than it, right? So that's what it means to have this being the rth small. Okay, so this is our goal. We want to find a number that's roughly in the middle. So our first try could be, I know divide and conquer, right? So if I want to find a number that's roughly in the middle, I'll say, okay, I'll just solve a smaller problem where I'll just pick n by 2 of the numbers, find their median. Okay, and what does that mean? So I have this full array a0, a1 up to an minus 1, and I pick, let's say, the first guys, and then I find the median of these guys. So this is guaranteed to be okay, right? So this one will have n by 4 numbers on the right and n by 4 numbers on the left. Okay, so this is the property that we wanted. Okay, so if you sort this, the median of these guys, if you sort the full array, the median of these guys will be somewhere here, and it will have n by 4 numbers on the right and n by 4 numbers on the left. Okay, so this is fine. So, yeah.
So why is that n by 4? Like, have we fixed the middle range or what?
No, I have not fixed anything. I'm just trying out random things, right? So I want to say, how do I find a number that is roughly in the middle? Okay, and and formally what I want to find is some number such that in the full array you have n by 4 numbers smaller than that array and n by 4 numbers bigger than that number. Okay, so and one easy way to arrange for this is to say, okay, I'll take n by 2 numbers and I'll pick their median, and I can pick any n by 2 of these numbers, and it's guaranteed to have this property. Okay, so but there's a catch here, right? So the catch is that to find the median, so even if you just recursively do things, okay, so this is going to take time t of n over 2. Okay, because there's an n by 2 size array of which you're trying to find the median. So this ends up giving you this recurrence where you get t of n is smaller than or equal to t of n by 2 plus whatever you got before. Right, so plus this t of 3n by 4 plus O of n. Okay, but this, it turns out, is actually very bad. Okay, so this is so any simple reason why this is bad?
Because we just sorted array finally.
Sorry?
We just sorted array finally.
No, so that's okay, right? So I'm just saying I'll recursively do this. For this part, I'm going to just recursively solve this smaller problem. Okay. So it's like the standard divide and conquer thing. I just solve a smaller problem, and this will allow me to find some number that's guaranteed to have n by 4 elements on either side. Okay. So the algorithm is correct for sure. Okay, we just want to analyze its running time.
More than n log n.
Yeah, this is much more than n log n, because last time, if you remember, we saw a recurrence whose solution we saw was n log n. That recurrence was you had n by 2 here and n by 2 here. Okay, and if that solved to n log n, there's no way this can solve to something smaller than n log n, right? Because this has a 3n by 4. So I just want to illustrate to you how you think about these things. Okay, so in recurrences, you don't have to literally solve every one to figure out what the thing is. Sometimes you just compare. Okay, so there are things you know, and you just say, oh, okay, looks worse than that. That itself was n log n. So there's no way this can be better. Okay, so this doesn't work. So, but this gives you a hint, right? So this says that if you want to solve something recursive, if you want to do some kind of a divide and conquer type algorithm, you've got to kind of reduce this running time to something significantly smaller. Okay, so this time for computing this n over 4 type element, this rth element, has to be significantly smaller than something like t of n over 2. Okay. And in the homework, we'll see how you will try to do this. Okay, so the idea is, it's this very tricky idea. So I'll actually spell it out and have you just work out the detail. Okay, so what you will end up doing is, you will divide the numbers into groups. Okay, so you have this a0, a1 up to an minus 1, and what you'll do is kind of divide this into groups of some constant size blocks you will do, and play with these blocks. Okay, so in some sense sort these blocks separately and then you do. Okay, so I won't get into that. That will be part of the homework. So, all right. So let's move on. Okay. So one thing I wanted to say was the algorithm that you will come up with. Okay. So the running time will have. It will actually look very similar to the running time we came up with, but it will have slightly better term. Okay. So it will have. You will get t of n smaller than or equal to t of n by 5 plus this t of 3n over 4 plus O of n. Okay. So instead of this n over 2 here, turns out this trick will help you get n over 5. Okay. And that it turns out is good enough. Okay. And let me just, I thought I should show you how to do things like this too, because it's this is slightly non-standard recurrence, right? So anybody has hints of how to solve this? So you can draw the tree, you can do a lot of calculations, but you know, it looks, these two don't even have the same denominator, right? So it looks very messy. Okay. But so I thought I should use this as a good opportunity to illustrate the ultimate cheating trick. Okay, so which is, you know, you want to show this is linear. Okay, so let's say I know some, instead of O of n, let's say I have some concrete number. So let's say I have some alpha times n. So ultimately I want to prove that this is linear. Okay, and the only way I know to prove is by induction. Okay, so suppose I wanted to construct an inductive proof, okay, that t of n, so suppose I want to show by induction that t of n is smaller than or equal to some c times n. Okay, where c is some big constant. Then what do I need c to be? Okay, so this is you should think of it as what mathematicians do on scratch paper. Okay, so what they write on real paper will be very different from what they do on scratch paper. Okay, so the trick to doing math is to learn what to write there. Okay, so let's see. Okay, so suppose I had to inductively prove that this is true. Okay, so then what will I do? Okay, I'll start by assuming this is true for. Assume true for numbers less than n. So this is the inductive. Suppose base case I proved somehow. Okay, so base case is like constant sized instance, so it will always take constant time. Okay, so base case is fine. And inductively I'll say, okay, I'm assuming it's true for all numbers less than n. Okay, and then I know this recurrence, right? So I know that t of n smaller than or equal to t of n by 5 plus t of 3n by 4 is 4, okay, plus alpha n. Okay. Okay. And I want to make this work out. Okay, so n by 5 is smaller than n. Okay, so I know that this is smaller than c times n by 5. Okay. Now I know that this is smaller than C times 3n by 4. Okay. And this is alpha n. So if this proof has to work out, then I should have that these three numbers, C times n by 5, 3n by 4 and alpha n, have to add up to smaller than C times n. Right? If I manage to have that, then I would be done. Okay, so in an inductive proof. Okay. So what should I do? So okay, so let's solve for this. So what that means is C by 5 plus 3C by 4 plus alpha times n. Okay. This should be smaller than or equal to C. Right? So Cn. Yeah. Okay. So good. So now okay. So now we have something easy, right? So now we have to make sure this holds. And okay. So what do we need to have for this to hold? So luckily for us.
So that's 19 by 20.
Yeah. So luckily for us, this is 19 by 20 times C. Okay. And you have this plus alpha, and you want this to be smaller than or equal to C. Okay. And this means that C must be bigger than or equal to 20 alpha. So luckily for us, this coefficient turned out to be positive. Okay, so if you try this proof as an exercise, go home and try this proof with the previous recurrence we had, where you had an n over 2 here. Okay. You'll see that this coefficient of C on the left will actually be bigger than the coefficient of C on the right, okay, which means that there's no C for which it can work. Okay. So it's good to try these things. Okay, so then you will see that C has to be bigger than or equal to 20 alpha. Okay. So now you can boldly write an inductive proof where you say that okay, I'm going to claim by induction that T of n is smaller than or equal to 20 alpha n, and your proof will nicely work out. So so this is how you figure out the detail. Yeah.
But by that you are actually saying that for this recurrence there is an algorithm which could be linear, provided that C greater than or equal to 20 alpha.
Yes.
So every time, so your alpha could actually change as I run my algorithm in a different environment. So
What do you mean environment?
So suppose I have say an AMD machine and I have an Intel machine.
Right,
so
but the fact that it's O of n means that for any architecture, you have some constant alpha.
Where you have a possibility of a linear algorithm that
Right.
you can implement.
So this is exactly the reason that so note that the implementation does not depend on C.
Okay.
You don't have to know C to implement it. This is just the proof.
Right.
Okay.
So
So
it just proves existence of a linear algorithm.
not really. So we gave an algorithm.
Right.
We are trying to analyze its running time. Okay. So now what we are saying is there is some linear bound on its running time.
Okay.
Which basically means the same algorithm runs in linear time.
Okay.
So it's roundabout in the sense that ordinarily this proof would be presented by saying, suppose that O of n term you can bound it by alpha n. For any system architecture there will be some alpha. Okay. Then you say that I will prove by induction that the T of n is smaller than or equal to 20 alpha n. Okay. And that proof will work out. Okay. But then that will leave you wondering how the hell did they come up with 20 alpha n, right? So, and this is supposed to show you how you get those numbers. Okay. So is that clear? Okay. Yeah. So, okay, yeah.
How did you get the 20 alpha n on the right side of that comparison? I'm sorry.
Oh, here it was just that if you subtract, so this is just basic algebra, right? So this is C by 20 must be bigger than or equal to alpha, which means that C is bigger than or equal to 20 alpha. Yeah. Yeah.
So basically it means that as we make smaller groups, the chance is more that it will be of the order of n.
You mean this n by 5 will become bigger? Yeah.
So the array is, we have divided it into, it was n by 2, so then it failed.
Yes.
The negative. So constant was negative. So when we made 5 parts, it was like
Groups of 5 actually.
Yeah, groups of 5.
Yeah. And so you could think of that n by 2 as just 2 parts.
Yeah.
Okay, and there it doesn't work. But if you think of it, if each group size is like a constant and a big enough constant, anything bigger than 5 works, as you'll see in the homework. This kind of reasoning will work out. So, yeah.
We get the t of n over 5 because the group size is 5, right?
Yes.
And then how do we get the 3n over 4 for the second element there?
Oh, this was always there. So note that, so this was what we said before, right? So this was, I told you in this thing that suppose I tell you the rth smallest element for r in that interval.
So
Okay.
are we guaranteed though that it's going to be that interval?
So the proof that you will do in your homework will guarantee you that after t of n over 5 steps, you will come up with some element that's guaranteed to be the rth element for r in this range. And that's why, so yeah. Yeah, that will be that.
So the thing is that we will be having n by 5 groups of 5.
Yeah.
So for each group we have to find median.
Yeah.
So the time for the first group will be n by 5 will be
No, so t of 5. T of 5 is a constant. But anyway, this is all part of your homework, so let's okay. So, other questions? Yeah. Yes.
Come up with the running time bounds when something like 1.5.
Yeah. So, you mean how do you guess that it is sent to the 1.5? So, very often you just like try it for a few, try expanding the tree a little bit and you get some intuition. Okay? And then you prove it by induction. Okay? So here this proof will work out even if I set n to the 1.5. Okay? But that's fine. It should, right? Because n to the 1.5 is bigger than, much bigger than n. Okay? So it will work out for anything bigger. The point is, what's the smallest thing for which you can make it work out? Smallest running time for which you can make it work out. Okay? So that's why here also the C you could set it to be 100 times alpha. Okay? But you would like to set it to be just 20 alpha because that's the smallest thing for which it will work out.
My point is, how can you guarantee that n is the upper bound? It might have minus or something n to the power 0.5 or 0.9.
So that's a good point. So suppose I tried this proof with some C times n to the 0.5. So that's actually a very good question. So you've got to, that's probably, let me try showing it to you why this fails. Okay, so you won't be able to find any C such that this is true. Okay, so let's try to guess that. Okay, so I have this recurrence where I get t of n less than or equal to t of n by 5 plus okay, so alpha n. So in this case, putting n to the 0.5 doesn't make sense because of that alpha n term. Okay, but suppose we actually had okay. So that would obviously fail, right? So let's try something slightly better. Okay, so suppose you had I don't know. Suppose you just had constant. So even in this case, you'll be able to get actually a slightly smaller power of n, but not just n, not just n to the 0.5. Okay, And this you can try to work out by saying, suppose I want to say that t of n is smaller than or equal to c times n to the 0.5. Okay. Then you can plug this in here, and then you'll say you'll have to have c times n to the 0.5 is less than or equal to 1 over 5 to the 0.5. So let's say I cancel out this plus c plus c times 3 by 4 to the 0.5, and plus in this case you will have 1 by n to the 0.5, which you can kind of ignore. Okay, so it drops as things increase, as n increases, right? So let's say you don't have this. But one thing you can verify is square root of 1 over 5 plus square root of 3 by 4 is actually bigger than 1. Okay. You can compute these and verify. Okay, so you can't have a C for which this holds for large enough n. Okay. So yeah, since this is a diversion, let me just end it at this. Okay, so turns out you can't do these kind of things. But this is a good way to test. Okay, so you have a guess, and sometimes your guesses will be wrong. Okay, and you just have to increase your guess and try doing it. Okay, so good. So this is what shows that you can do median in actually linear time. Okay. So that's the full proof. I mean, assuming the homework bit. Okay, so now, so it turns out we have a little bit less time than I thought. So let's move to dynamic programming. Okay. So firstly, I'll just do the simple example that I have in mind. Okay. So dynamic programming, for those of you who've seen it also, is just recursion done well. Okay, so that's how you should think of dynamic programming. Okay, so ordinarily you think of coming up with an algorithm recursively, and you observe that, oh, okay, maybe I can do things better. Okay, and that's how you should think of dynamic programming. Okay, so that's one line. So okay, so let's see. So let's start with some easy recursive algorithm and try to see what's going on, try to see how you can fix it. Okay, and that will give you the first illustration of dynamic programming. So this is a very simple example, but I don't know, I think this is the easiest illustration of dynamic programming. Okay, so this is an algorithm for computing Fibonacci numbers. So what are Fibonacci numbers? So these are numbers which go like this. Okay. And the property you have here is that every element is the sum of the previous two. Okay. So this is the definition of Fibonacci numbers. They start off with 1, 1. And so you have f0 equals f1 equals 1. And you have fn equals fn minus 1 plus fn minus 2. Okay, so this is the definition of Fibonacci numbers. And now the question is, suppose I give you n, given n, compute fn. Okay, I want you to come up with an algorithm for this. So this is definition of recursion, right? So you just say, oh, okay, this I write this function which I call recursive Fibonacci of n. If n is smaller than 2, I just have to return 1, because for f0 and f1 the answer is 1. And otherwise, I return Fibonacci of n minus 1 plus just make a function call with n minus 1 and n minus 2. Okay. So for those who haven't seen this example before, what could be the running time of this algorithm? So either all of you have seen it or okay. So okay, yeah, then in general, so what could be the running time of this algorithm? Any guesses? So if we don't know, we should just draw the tree, right? So we should draw the recursive tree. So let's do that. So we have this, let me just call it FIB, okay, so of n, and what it was doing was it was calling, so n minus 1 plus r of n minus 2, okay? And it was adding the two answers that you get. Okay, so you have that t of n is equal to t of n minus 1 plus t of n minus 2 plus 1. Why the plus 1? Yeah, you're adding and returning something, right? So that's plus that. Okay. So what does this solve to? If you observe, this is very much like the Fibonacci number itself. So it just is, except for this extra one. Okay. So question is this polynomial? Is the answer to this polynomial? Is it linear? What's that?
Not linear.
Yeah, this turns out to be exponential. Okay. And how do you see this? Any easy ways of seeing that it should be exponential? You can solve it, it will take some time, but turns out you can find a closed form. But again, you can use this trick that we saw some time ago, where you just say, okay, look, if I didn't have n minus 1 plus n minus 2, but if I had bigger than 2 times t of n minus 2. Okay. So even this is exponential, because this is like 4 times t of n minus 4, and in general you have 2 to the n minus k times t of n minus 2k. So this will tell you that this is bigger than 2 to the n by 2. Okay. And this is exponential. Okay. So it takes n by 2 steps to go down to 0. Each time you get factor of 2, and that's why you get 2 to the n. So this is exponential, right? Because if you manage to do it. Okay. So this seems bad because you have this function that you want to find. Looks simple enough, but takes exponential time to compute. Okay. So how can we do? What can we do to speed up this process?
Store the partial.
Sorry?
Store the partial, because we are doing recalculating every time. Like
Yeah, so that's the main observation. Okay, so for most people might have seen this. So basically, what's going on here, right? So it's not the way this is different from what we've been doing so far is earlier we had recursive calls, but the arguments for these recursive calls were something complicated, right? They were arrays and so on. Now the arguments are simple integer numbers. Okay, so these are the arguments to this recursive call. Okay. And there are very few of them, right? So what you can do is, so you observe that, okay, when I call rfib of n minus 1, it's actually calling rfib of n minus 2 plus rfib of n minus 3. Okay. And here it's doing rfib of n minus 3 plus rfib of n minus 4. Okay. Now you observe that, okay, there's just the tree just overlaps in too many ways, too many places, right? Like here I'm trying to compute something, and the same number is being computed here. And the same with this and this. Okay. So there's too much recomputation. Okay, so there's a lot of redundant calculation. And this is what I mean by recursion done correctly. Okay, so basically you observe what's going on in the recursion. You observe that you are doing a lot of calculation you don't need to do. Okay, and this is the idea. So what you can try to do is you can just try to memorize these numbers. Okay, so just store rfib of n. No. So in this case, whenever you compute it, okay, you have an array, okay, extra array. So rfib values whenever you compute them. Okay, and that works. So this means that you can avoid recomputation. Okay, and in the code, what modification do you have to do? Store is fine. Yeah, at the end you've got to store. Okay, else instead of returning while returning you also store it into an array. So set a of n to be equal to this answer. Okay. There's something else you have to do.
The second term gets looked out from the
You could do that, but in general you could always just say, you know, before when I try to compute something, check if it already exists. Okay. So check if a of n, initialize everything to some undefined value. Okay, so like -1 or something, and then you just check if an has been computed, then just output whatever has been computed. Otherwise, you do this casually. So this is a simple way. And what's the running time of this? It's very tempting to say n, but you have to think more carefully about it because turns out these numbers actually grow in size. Okay, so when you add fn is roughly an n-digit number. Okay, so when you do fn minus 1 plus n minus 2, you're actually adding some numbers. So if you do like if you look at this addition for like from n by 2 to n, you're doing a whole bunch of additions. So you have to be careful with these things. Okay, so let's not go there. Okay, so this trivial algorithm turns out to have n squared type running time. But yeah, let's not go there. But essentially the number of recursive calls though is in terms of just the number of calls, it's linear, right? Because you don't compute anything more than once. Okay, so good. So this is the algorithm with memorization. This is what we just said. And okay, so one other thing to keep in mind when doing these things is, are we wasting memory? So in particular, do we really have to store all the n numbers that we've computed so far? Yeah, so what you would instead do after seeing this is, you know, for computing fn in this tree, you just needed to know what f of n minus 1 was and f of n minus 2 was. Okay, but if you do it this way, okay, then if you do it via recursion, then you know, you're forced to keep track of these things because f of n minus 1 will try to query this and so on. Okay, but this motivates a very simple alternative way of doing things, right? Which is you just do things bottom up. Okay, so this is this other thing that you should think about dynamic programming, is that sometimes you might want to think top down but implement bottom up. Okay, so that's one thing to keep in mind. Okay, so you start off compute bottom up. Okay. So this is no longer a recursive algorithm. Okay, so if you think about it, it's very nice. Okay, so we thought about this algorithm in a recursive way, then we are actually implementing it in an iterative sense. Okay, so it's nice. So okay, so you start off by computing f0. This you don't have to compute. f1 equals 1. Then you compute F2 using just these two. And every time you just keep track of the two most recent things and you update. So, keep track of okay, so let's not get into the details. It's very straightforward. But the moral is something that you should keep in mind, which is you think recursively but implement bottom up. Okay, so think top down. Implement bottom up. Okay, and sometimes just this memorization type algorithm works just fine. Okay, so doing this doesn't give you much more of an advantage, but it's good to keep this in mind. So this is so any questions about this Fibonacci example? Meanwhile, let me go to the next slide. Okay, so this is the general view of dynamic programming that I've been saying so far. Okay, so you think of it as recursion but done correctly, without waste. And this is the other thing. Okay, so sometimes to save memory, you might have to just implement bottom up. Okay. Could be more efficient than just memorize it. Memorizing answers. Okay. So yeah, and the way you come up with a recursive algorithm is usually just say, oh, okay, I can reuse computation, you remember that. And this again, as I said before, you should be aware of memory usage. This is the first, so many algorithms which you will see will have quadratic memory usage. Okay, and that is usually not great. Okay, so you want to have, for some problems, actually for some problems it's unavoidable. Okay, and for some problems you can avoid it. Okay, but this is good to keep in mind. Okay, this is one of these rookie mistakes people at companies do. They define this, they know dynamic programming, and then they try to define a 10,000 by 10,000 array or something like this, million by million array, and it runs out of bounds. Okay, so be aware of what you're doing. Okay, so other example I wanted to do, I have 5 minutes, right? Oh, I have 10. Okay, then maybe we can do this. Okay, so it's called longest increasing subsequence. Okay, so this is again a numeric problem like the ones we've been doing. So you have this array. Okay, so a0 through n minus 1, and what you want to do is you want to find an increasing subarray. So it doesn't have to be a contiguous block. Okay, so a subarray of this could be this, 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 and this. Okay, so you just have I picked out 4 elements. Okay, so this is a subarray. You could also have something else like this. Right? So this is a subarray. So all I mean is go from left to right, pick a subset of the elements. Okay, pick some of them. And you call a subarray increasing if the numbers are increasing in order. Okay, so like this bottom subarray, where you pick this, this, and this, is increasing. Right, because it's 9, 16, 21, 32. Well, the top one is not. Okay, so it has 13 and then 7. Okay. So this is an increasing subarray. And the goal is you want to find a subarray which has the largest possible size and it's still increasing. So this is the problem. So in this case, so this is an array of size 4 and increasing. Okay, this is, maybe if I include this is size 5 but not increasing. So you want the largest possible size and you still want it to be increasing. So in this case I haven't computed what the answer is, but I think it's 4. Okay, so I don't see a bigger array. Yeah, I think it's 4. But okay, so how do we find the longest such array, which is increasing order?
How is it 4?
I haven't told you why the largest is 4, it's just that I couldn't find. Okay, so it could be large. So that's part of the thing, right? So you have to reason about why it is 4, but we haven't done that yet. Okay, so for all you know, there could be 5. Okay. So how would you go about doing this, right? So suppose I gave you an array and I told you, okay, so find me the largest increasing one. So, you could try, right? You could just start by coming up with increasing subsequences. You can say, oh, okay, let me start at 45 and, try to see if I can find an increasing subsequence. So that turns out to be a rather unfortunate choice because there's nothing bigger than this. Okay, so the largest increasing size only 1. Okay. So then maybe you'll say, oh, okay, let me start at 9 and then start doing some search. But you'll quickly find that there are exponentially many things you have to search because the number of subsequences is a lot. Okay, so subarrays is a lot. Okay.
You could do it bottom up again.
You could do it bottom up, yeah. Or you may think that, oh, maybe there's some clever way where I start with the smallest element, do something.
Yeah, on the side, that is, you start with a subarray of size 1 with one element, and
Okay.
then you look at the other elements and see if they can be added to.
Yeah, so that is one thing, right? So maybe you start with, but even so, there are lots of subarrays of size k because you can. It's not. They don't have to be contiguous. So that's one. Yeah, so that's an issue.
We can just track that which from the elements which is the largest one. Like
Yeah, so that's a good start, right? So one question you could ask is, suppose I tell you I want the longest subarray that starts off here. Okay? What you are saying is ending somewhere, but it's the same symmetric thing, right? So let's say I say, okay, I want to see what's the longest subarray that starts off with this 9. Okay.
9, 16.
So take the longest subarray of the remaining.
Yeah, so we could try to come up with a recursive algorithm that works like this, right? So if I just want to find the largest subarray in the whole thing, then I could say, okay, I'll find the longest subarray starting with this guy, then I'll find the longest subarray starting with this guy, then I'll try this and so on. For each one there will be some longest subarray. Let's say I do it recursively. And then I just output the maximum of these lot. Okay. So let me write this recursive algorithm. So let's call this subarray of 0 through n minus 1. Okay. So this is the function call that I'm trying to write. And what I'm saying is, okay, so try solve subarray of 0 through, okay, this is so subarray of
1 to n minus 1.
Sorry?
You could solve for 1 to n minus 1 and then see if 0.
No, so I have to be a little bit more careful. Okay, so let's see. So suppose I want to find what is the longest subarray which starts with 45. Yeah.
So essentially we might not do this for the whole array. We can do it say for like 0 to n by 2. So
Yeah.
that because since this is an unsorted array, the chances of having a array with more than n by 2 items in the right half of the array will be less.
Okay, why is that?
So say this is a let's take this array as an example. So usually we know that the array starting with 9 is the longest array.
Yeah, but we don't know this, right? We don't even know the numbers.
Yeah, we don't know the numbers.
Yeah.
Since this is an unsorted array. But say if 9 is on the right half of the...
You're saying that it's unlikely that the starting point for the biggest thing is, but you don't know that up front, right? Like for all you know, like the largest subarray, so here you could have been very lucky and you start out with 1, 2, 3, 4, 5. Here you could have had like 41, 32 and so on, which are kind of bad.
Yes.
So you don't know that the array doesn't look like this. And in this case, it's actually better to start off in the second half and look. Okay. So I agree, it's unlikely, but for all you know, it's not guaranteed to work.
Yeah, but if we find a subarray in the first half, which is more than the number of elements in the second half, then there's no way that there can be a larger array in the second half.
That's true. So you can prune out, if you find a really long array, then you can prune out a whole bunch of things towards the right. But you can convince yourself that even that takes exponential time in the worst case. Because usually the longest sequence won't have length that is like significantly big. It could just have like root n or something like that. In which case you won't be pruning out too much. Okay? So we'll see next class how to do this thing. Okay? The idea is, try to figure out starting at some point what you get.
So,